All right, class. This is the second in two videos from 7-1 in our textbook on equations and inequalities. Now we're going to talk about the newer type of thing for you guys, which is dealing with inequalities. Now, you have dealt with inequalities before, because I know you guys have seen some of these symbols like less than and greater than, but the two newer ones for you guys are going to be less than or equal to and greater than or equal to. And that's how you pronounce them, as it says right here. What they mean is you can have an answer that is no more than a certain amount or no less than a certain amount. Before, you always had something was always smaller than or greater than, but now you can have a second stipulation. And we're going to discuss that some more when we get into some of these examples. So let's just redefine what an inequality is. An inequality is a mathematical sentence that compares quantities or amounts of things using less than or equal to, or greater than or equal to. And the table below just goes ahead and redefines those symbols for you and gives you some explanations on what they mean. But like I said before, the best way to do this is to actually just jump right into the work, and we'll explore what these signs mean as they pop up. So I'm going to go ahead now and scroll down to our first example, or not our first example, but our third example from this section. Now, example 3. Just like the last one with equations, the rules are identical. Here we are asked to determine if -4, -5, and or if -6 are solutions for the equation 7 minus 2x is less than or equal to 15. It's less than because of the little arrowhead, and the half of an equal sign gives us the equal to or equal to part. So I'm going to go ahead and just black out, or white out in this case, I guess, everything on this page so I have a nice clean space to work with. And I suggest you guys do the same thing on a separate sheet of paper. Let me go ahead and fill this in, reposition, and now we can get to work. So we have a first value that we're given to use to substitute is -4. So I will begin by writing my algebraic expression. 7 minus 2x is less than or equal to 15. Now we are going to plug in the -4, and we have 7 minus 2 times -4, which is less than or equal to 15, or we're hoping to see if it is less than or equal to 15. Now, this is also a two-step equation. I have subtraction right here, and a number next to another number that's separated by parentheses also indicates multiplication. So, following the order of operations, I know multiplication comes first. So I'm going to go ahead and write down the 7 and minus, and then I have to work with this 2, because this is a positive 2, times a -4. 2 times -4 is a -8. And then I'll go ahead and just recreate the rest of the equation. Now I have to do my subtraction. Here I have subtraction, but I remember from chapter 1 I learned about something called the additive inverse. That tells me I can turn subtraction problems into addition problems, which I find a lot easier. The rules for the additive inverse was the first number stays the same, subtraction turns to addition, because that's the whole point of the additive inverse, and whatever your second number is has an opposite sign. So if this is a -8, the opposite becomes a +8. Now I can get right back to work. 7 plus 8, which is really easy to do for me, is 15. Now 15 is not less than 15, but it is equal to 15. So -4 is a solution. It makes the equal part of the solution of this expression or equation true. This little line on the bottom. Now let's try our other answers and see how they affect our equation. So my next number I have is -5. I will start by writing my algebraic equation first. 7 minus 2x is less than or equal to 15. I will substitute my value of -5 wherever I see an x. 7 minus 2 times -5 is less than or equal to 15. I will follow the order of operations, or PEMDAS, and I know that multiplication will come first. So 2 times -5 is a -10. I bring everything else down. Now I have 7 minus -10. Once again, I'll go ahead and use the additive inverse. Subtraction turns to addition, and my second number becomes the opposite. If it's a -10, it becomes a +10. Getting back to work, 7 plus 10 is 17. 17 is not less than 15, nor is it equal to 15. So because this is not a true statement, it's false, then -5 is not a solution. And I'll go ahead and retrace my steps again and check my third value now. So I have -6 now. So I'm going to go ahead and write my algebraic expression. 7 minus algebraic equation is less than or equal to 15. I'm going to go ahead and substitute my value negative 6 for my variable x. 7 minus 2 times negative 6 is less than or equal to 15. I'll go ahead and follow the order of operations once more. Multiplication will come first. 2 times negative 6 is negative 12. I will apply again the additive inverse, subtraction. This becomes positive. Continue with my addition. 7 plus 12 is 19. 19 is not less than 15, nor is it equal to, so negative 6. So this is kind of like the first two examples we did before. It seems very similar. I have one answer. The other two I proved can't work. So what's the big deal with inequalities? How do they really work? Well, I think we're going to see that now in the next example. And as always, when I go through these examples, if you have any questions, feel free to write them on the side, and either on the page, or write them on the page actually. And that way in class tomorrow, before we begin going into the lesson, you can ask these questions you might have, and we can get to the bottom of it right away before there's any issues. Now, let's go ahead and look at number 4. Once again, I'm going to follow white everything out. All this stuff gets a little too busy for my eyes, and I just need to concentrate and see what's really going on here. So let me go ahead now and examine number 4. It tells me to determine if 15, 24, and or 27 are solutions of 5 minus m over 3 is less than negative 2. They give us the 3 values. Our variable is g. It says value of g. Interesting, they use m, so the value of m, I guess, here. Our variable is m, and that's what's going to be changed out for each one of these different values. So let's go ahead and just begin the process as we did before. We have 5 minus m over 3 less than negative 2. Many of you have already proved to me or showed to me that you know that whenever you see a fraction bar, that is division. We have division right here with the fraction bar and a subtraction sign. So indeed, this is a two-step equation. Following PEMDAS, I know that division will always come first. So now let me go ahead and substitute my value of 15 into this equation. Following PEMDAS, 15 divided by 3 is 5. And then I have 5 minus 5, which is 0, is less than negative 2. Well, to prove that I know what the answer is or what I'm talking about, I'll go ahead and refer to a number line to prove my case. Is 0 less than negative 2? Well, here's 0. Here's negative 1. Negative 2 would be right here. Well, 0 is to the right. All numbers to the right of any are always bigger to the numbers to the left of them. Just like all positives are bigger than negatives, 0 is bigger than any negative for sure. So the statement that 0 is less than negative 2 is false. Therefore, 15 cannot be one of our solutions. For these problems, I'm going to go ahead and explain with a number line to give you guys a better understanding of what the answers are really saying. So let's go ahead and go on to the next example. Or not next example, the next part of this example, excuse me. Now, let's go ahead and change this up. We have the value 24. Once again, I'll write my algebraic equation. 5 minus m divided by 3 is less than negative 2. I'll substitute for the letter m, or the variable m, the number 24. And I'll go ahead and begin with PEMDAS. Order of operations, 24 divided by 3 is 8. 5 take away 8. 5 minus 8 is this. I would subtract 8 minus 5, which is 3. I have more in the negative side, so I have a negative 3. The statement is negative 3 is less than negative 2. Well, if I refer to a number line, here's 0, here's 1, here's 2, here's 3. Well, negative 2 is right here. Negative 3 is right here. Negative 2 is to the right, so it's bigger than anything over here. So negative 3 being less than negative 2 is a true statement. With negative numbers, it's like the opposite. The bigger they look, the smaller they really are in place value here. So this is a true statement. Now let's go ahead and do our last value. And for this one, I guess I'll switch it up a bit. Use this one. And we begin with our equation once again. 5 minus m divided by 3 less than negative 2. 5, substitute the m for 27 divided by 3 is less than negative 2. Following PEMDAS, 27 divided by 3 is 9. 5 minus 9 is a negative 4. We want to know, is negative 4 less than negative 2? Here's 0, 1, 2, 3, 4. So here's negative 2. Here's negative 4. Negative 2 is on the right of negative 4, so anything to the right is always bigger than what's to its left. So this is also a true statement. That means you can have, with inequalities, you can have more than one answer that makes the whole thing true. With equations, you generally just only have one answer. But inequalities, you can have 1, 2, even an infinite number in many cases. Or you can even have a select range. It totally depends on the type of equation given. But here we saw, out of these selections, 2 of these made this whole thing true. So inequalities can have more than one answer. Equations generally have one, but there are exceptions, and you'll learn those when you get into upper level math. Now, let me go ahead and clear the screen out, and let's go down to the bottom of the page. Now you have these last 2 problems, C and D. These 2 are also assigned to you to practice and know how to do, because you will be asked to demonstrate this type of problem solving in class. So just to give you a little help here, this is obviously like example 3, and this is like example 4 that I just did. Determine if negative 24, negative 48, and or negative 72 are solutions of this expression here. Here you have division and addition, but remember you have a negative here, so you have to remember your rules for integers. I would suggest going back to chapter 1 if you don't, and look at your notes for those sections. Also, determine if 2, 4, and or 6 are solutions to this one. This one looks a little more probably friendly for you guys, but nonetheless, you have to know how to do both kinds. If you have any questions, please write them on the side, and in class, before we go on with our guided practice work, ask these questions. If not, we will just continue chugging along. Thank you very much, and good luck with your work.